Ladies and gentlemen, welcome to week 3. We are in the middle of chapter 2 or lecture 2 on high-dimensional data, and we're talking about chapter or section 4, feature reduction today. Sorry for this a little theatralische intro. I heard that good podcasters just use some intro jingle, and well, I'm not a good podcaster, but I'll try my best to become one. Yeah, so I hope you appreciate it. Anyway, so today, as I told you, feature reduction. So we'll talk about reference point embedding, so different methods of feature reduction in metric learning things. And we will begin with a short acknowledgement, because some of the slides are donated by Bernd Bischel's team, Bernd Bischel's group from the statistics department. I very much appreciate this one. Special thanks to Giuseppe Casaliccio, who actually gave me the material, and I'm happy to use it actually. So I changed it a little bit, but actually the IP, so to say, is on Giuseppe in that case, or Bernd's group. Thank you for that. So anyway, so the idea of now feature reduction is that, in feature selection, we try to remove original features to find low-dimensional feature spaces, but we kept the original features. Yeah? And now we try to not remove features, but try to come up with new features, find a lower dimensional feature space with typically new features, derive new features, that tries to somehow model or represent the original data space as accurate as possible, of course. Yeah, and that means we will try to take care again of these two different malicious types of features. The redundant ones, we will try to summarize them, aggregate them in some case, which is a kind of new feature then, because we derive a new one or several new features from redundant features by just summarizing or aggregating them. And we also try to get rid of the irrelevant features. So here different strategies exist actually. So sometimes we try to just weight those by small values, or we even try to really erase them, delete them. Yeah. So the best case, of course, we want to get rid of them completely. So the new feature space, in the best case, should contain no irrelevant features anymore. But sometimes, since we just aggregate the irrelevant features or sum them up also, like the redundant ones, they are not really erased, but somehow weighted at least smaller, so that they don't bias my data mining problem, my algorithm, my solution, and especially the curse of dimensionality should be eased. So here are some sample methods. There are a lot of methods for doing feature reduction and metric learning. We just cover a couple of them. So a very simple one we'll start off with will be the reference point embedding. Then we will have a look at principal component analysis. Once again, the acknowledgement to Bernd and Giuseppe on that. In that case, a generalization of PCA is the singular value decomposition. We will have a look on that. And then we'll have some closer look on different model-based feature reduction techniques. One is called the Fisher phases. A second one is called relevant component analysis. And last but not least, we'll have a look at the so-called large margin nearest neighbor method. Once again, this is really a very, very brief snapshot on how you can do feature reduction. There's a lot of stuff out there again. And once again, since this is a kind of pre-processing step, think about the whole big picture. We are more or less in the pre-processing step. So if you do something shitty here, you get shit, and if you put shit in, you will get shit out. Sorry for using this sh word so often, but you know what I mean. So you have to really take care that you don't do something wrong here, because if you end up in a data set which is, shit, then the data mining algorithm or the machine learning algorithm or whatever kind of algorithm will produce again, you know what? Yeah, I know. Okay, so the goal now is, as I told you before here, we try to remove features, find a lower dimensional feature space, not necessarily or typically not a subset of the original features, but some kind of new features that try to represent the original data space as accurate as possible. And so we want to describe the data with fewer features, reduced, in other words, the number of columns, if we think of the data set as a table where the columns are the features, of course. So if we want to reduce the features, reduce the data, you have to be clear, or we have to be clear, that there will always be an information loss. Of course, that's always the case. Also in the previous section on feature selection, we had some information loss, and we will try, and in this section, the feature reduction methods will try to minimize this information loss, whatever that means. And in whichever direction you can minimize the information loss, depending, of course, on how to model information loss. Information loss maybe on this slide is some kind of abstract thing. And of course, all those feature reduction methods, will try to come up with a different idea on information loss. And also be sure that there are some supervised methods which really need to have labels, but there are a lot of unsupervised methods. For example, PCA is unsupervised, so in that case, the methods do not care about any class labels, or can even also work without class labels, which is good actually. So most of the feature selection methods we got to know last week are usually in the supervised setting. So here we are now also a little bit more in the unsupervised setting, or at least we can somehow play the unsupervised setting. So the first one I want to tell you about is, as I told you, a very simple thing, which is called the reference point embedding. So what is the idea? The idea is you describe the position of each object by their distances to a set of reference points. So you just take a set of reference points, and then you measure the distance of each point to these reference points. And these distances are the new features of each of the points. So a little bit more formally, you have a vector space, n-dimensional, and a k-dimensional space is the target, which yields an optimal solution for a given data mining test, of course. But now what you're doing for each reference point, so you just say, okay, I'm the big spender here. I spend a set of reference points, k reference points, because you want to end up in a k-dimensional space. So you say here are k reference points, random, whatever, and now you measure with a distance measure for each vector of the original feature space, of the original data space. So X is one original data object, and then you just measure all the distances of X to all the K reference objects, to all K reference points. So, and each of those distances form one of the new dimensions of the new features in the target space. So the space R will be the distances to the reference points. So here you probably see a kind of visualization here where R is just one reference point here, and what should be hopefully visible here is that you may have two patterns, blacks and whites. So politically completely incorrect, but anyway, so you have these two classes or clusters. And if you embed those points with this reference point embedding, you end up in a one-dimensional data set, because you just record for each of the points the distance to this reference point. So this guy gets as the new value this distance, and this and this and this. And you see that all the white guys have a very small distance or something else to the reference point, and the dark ones, black ones, whatever, have a large the distance to the reference point. Yeah, and maybe in the new one-dimensional feature space, you can really distinguish here between the two classes. Yeah, which is a little bit more complicated. I mean, still doable, but a little bit more complicated here in this one. So yeah, this is a very simple example that should show you that you can use this reference point embedding maybe to get a cool and a good and a meaningful feature space. So short discussion on that's all actually on this reference point embedding. There are a lot of variances on this technique, but they basically follow the same idea. So yeah, short discussion. Distance measure is usually determined by the application, so be aware that should maybe probably also go into the distance disadvantages, because if the distance measure is not good, then probably your embedding is also not good. Yeah, but anyway. Second one should probably also go into the disadvantages. Selection of reference points can be extremely important. Yeah, very often people try to use centroids of the classes if you have labels, or if you don't have labels, cluster it before with k-means and then use the cluster centroids. Yeah. Other people propose to use points on the margin, on the limits, at the borders of the data space. Some people just say use k-random samples, no problem. Try to distribute them uniformly. That's fine. So there are a lot of different approaches or proposals how to select the reference points, and that's why. And the reason is why that is because the selection of the reference points can be extremely important for the accuracy of the resulting data space. Yeah. Anyway, there are some advantages. So it's a very simple approach, very easy to implement. You just have to compute all the points to the distances to the reference points, which could be, well, kind of costly, but I mean that's pre-processing, so why bother? And the transformed vectors yields typically upper and lower bounds of the exact distances. You may ask the same question as here: what the hell is that good for? What the fuck is that good for? Well, that can have very interesting performance, say, perspectives. Yeah. So if you have upper and lower bounds, you can use it in some algorithms. You can use them to come up with so to prune candidates, for example. Yeah, to exclude candidates from further inspection. So that can be quite beneficial actually. Yeah, but that's more a kind of performance thing. Yeah? So the disadvantages, even using dereference points does not reproduce a d-dimensional feature space, of course. Yeah. So you never know what you get actually. And as I told you before, selecting good reference points and also selecting good measures, distance measures here, is extremely important, but also extremely difficult. And there's a lot of try and error with different reference point selections, which is a kind of meta parameter which you can try to optimize, of course. Yeah? So easy to implement, simple approach. Sometimes simplicity has some kind of beauty, but never underestimate the disadvantages here.